All right, so again, we're continuing on with energy, and this time what we're going to look at is power. Now, what power is the rate at which you can do work, which is adding energy to something, or the amount, or transforming energy. So it's the rate. It's how fast you can transform energy, or how fast you can do work. So an example, the units is, because energy is in joules, it's joules per second, which is most commonly or more commonly noted as watts. All right, so watts is joules per second. You probably see watts on a light bulb. It's how much energy that light bulb is using per second. So that's why I say a 100-watt light bulb is much brighter than a 60-watt light bulb, because it's using more energy to create light than the 60-watt. All right, so ironically, I didn't make this example up I made this example up a long time ago, but example one talks about Austin Matthews and Connor McDavid, ironically. All right, so it says, so we're going to have two different players here. So I'm going to write, we got Austin Matthews, and we've got Connor over here. All right, our two players. Now, it says Austin Matthews exerts a force on an opposing player of 200 newtons over a distance of 15 centimeters for 0.2 seconds. Now I'm going to back it up here because I forgot. There's two formulas that I'm looking at. Little forgetful. All right, so again, with power doing transforming work, the rate at which you're transforming work, what you're looking at is that power is equal to work divided by time. How much work do you do per second? And again, we looked at work being force times distance divided by time. Now, power is also how fast you're transforming energy. So this formula could also be delta E, how much energy you've transformed, divided by T. So there's our, two formulas, I would say, or you could look at it as three formulas. All right, so we definitely need some formulas, because now we're headed again to Austin Matthews here. Now, he exerts a force of 2,000 newtons. So I'm going to throw that down, 2,000 newtons. All right, over a distance of 15 centimeters. So our D is 15 centimeters. Again, that is not in our standard units, so I got to change that to meters. I'm going to have to divide by 100 because there's 100 centimeters in a meter. And so if I divide by 100, I get 0.15 meters. All right, and that force that he exerts on the player lasts for just 0.2 seconds. So there's our T. All right, now Connor McDavid, on the other hand, exerts a force of 1,750 newtons, all right, over a distance of 10 centimeters. All right, so again, with centimeters, I have to convert to meters to get into our standard units. So it's 0.1 meters, again, divided by 100. And that instance strikes for just 0.1 seconds. All right, so there's our two players, or two people, I guess you could say, that we're looking at. We're examining their power. And so I have the force times distance, and I have the time. And so I'm going to use P equals FD over T. All right, so I'm going to have to use it twice because we get two different players here. And so power, again, the force is 2,000. Our distance in standard units is 0.15. And our time is 0.2 seconds. And so we're going to actually do this all at once. 2,000 times 0.15 divided by 0.2, I end up with 1,500. And again, the units are watts. All right, so that is for Austin Matthews. Now we go over here to Connor McDavid. And again, using the same formula here, we have P. We have our force times our distance. So we're going to have 1,750 times 0.1. All right, and our time is 0.1. All right, and so if I 1,750 divided or times 0.1 divided by 0.1, I end up with 1,750, and again the units are watts. And so who is the most powerful player? Well, Connor McDavid has 1,750 watts. He is the most powerful player when we're comparing to Austin Matthews. Now, here's something interesting in sports, is that you look at the force. Austin Matthews does a 2,000 Newton force. Connor McDavid does a 1,750 force. So what is happening, and this often happens in sports, is that Austin Matthews is stronger. He's able to put more of a force on a player, but he's not more powerful. There is a difference between strength and power. And so you can be strong, but not powerful. And the combination to be powerful is that you have to be strong and fast. And that's what Connor McDavid is in this situation. He is not as strong, but he's faster, which actually happens to be kind of true. All right, so let's try a few more different examples. It's also why in sports, a little person, somebody who's smaller, can knock down somebody who's much bigger, is because they're more powerful. They add speed and strength. That's what makes you powerful. And if we were in class right now, we would have an activity, a lab, where we see who the most powerful person in the class is. There's an interesting lab doing that, but we can't unfortunately do that right now. All right, so let's get to, whoa, that's so wet. That's how I wreck my markers. All right, so example 2 here. A painter who's 85 kilograms climbs 2 meters up a ladder in 3 seconds. Not bad. Calculate their power. It's quite a ladder climber. All right, so let's see what we got here. We're looking for power. So there's my P. They climb up a height of 2 meters. All right, so 2.0 meters up a ladder. Okay, and what else do we got here? It takes 3 seconds. And we also know their mass, which is 85 kilograms. All right, now, here's the key with this, is that person who is, let's see, 85 kilograms here, they have to apply a force to go upwards. Now, that force applied that must happen has to counteract gravity. And so our applied force and our force of gravity are the same. And again, the force of gravity is m times g, which in this case we have an 85 times our 9.8 meters per second squared. And so our force of gravity, which again has to equal our applied force. So you have to counteract gravity to go up a ladder. Or if we did a lab in class, you'd have to run up some stairs, still having to counteract gravity. And so if I multiply 85 times 9.8, I get 833 newtons. All right, so for this person to run, that's a terrible N, to run up this ladder, they have to apply the force of gravity to move up this ladder. And so if I'm calculating the power of this person, I'm going to use force times distance divided by t. And again, our force is that 833 newtons. All right, our distance, well, our distance is we're moving upwards. So h and d are the same thing. It's just h is the distance upwards. So that is our distance we're covering. So a 2 there. And this happens over 3 seconds. And so the power of this individual, 833 times 2 divided by 3, is 555 point, again, going to two decimal places here, 555.33 watts. All right, so that is somebody going up a ladder. B. All right, so for the amount of work the painter uses to climb the ladder, okay, how long could they keep a 60-watt light bulb on? Okay, so how much work did they do here? Well, again, work is equal to force times distance. All right, and so we'll have to figure that out. Now, again, the force that you have to apply is 833 newtons for 2 meters. And so the work that this person puts in, let's see, I double that. Well, I double 8, it's 16. Double 33, it's 66. So the amount of work that this person does to climb this ladder is 1,666 joules. Now, we want to know how long you could keep a 60-watt light bulb on. So there's our 60 watts as our power. And we're looking for the time. Now, it took 3 seconds for this power to be used up to just raise this person up. But now we're looking at just keeping a light bulb on. All right, so again, I'm going to use my P is equal to W divided by T. All right, and let's see here. So our power source is 60. That's all the light bulb is requiring is 60 watts. All right, my work here is 1,666 divided by T. Again, I've had this many, many times. A number equaling a fraction. I like to go fraction equaling a fraction. And so I get 60 times T equals 1 times, well, 1,666. All right, and then the last step there is to divide by my numerical coefficient. Let's use a different color here. 60, 60, and so let's see here. So our time is 1,666 divided by 60. And because the power doesn't use or the light bulb doesn't use as much power, it's going to be 27.77 seconds. There we go. All right. Well, I've actually seen some gyms where they do that. They actually have a little light bulb on your treadmill or your elliptical. And so you start running slower, that light bulb gets dimmer. But in this case, that amount of work he used up, that amount of energy this person used up, took 3 seconds to climb the ladder. But the light bulb would only use, using the same amount of energy, would take 27.77 seconds to use up that much energy. All right, so we get to our last example. Here. All right, so the last one here, we have a truck, okay, which is 1,400 kilograms, is raised from the ground using a hoist to examine its exhaust system. That happens all the time. If the hoist has a power rating of 4,000 watts and took 5 seconds to complete the lift, how high was the truck lifted? All right, so here again, I'm going to write down my variables that I know. All right, so with example 3, we have a mass. This is a 1,400 kilogram truck. So that's roughly 3,000 pounds there. It has a power rating, this hoist, of 4,000 watts. Okay. It took 5 seconds to complete the lift. And we want to know the height. How high was this truck lifted? All right, so again, what I can look at is this object, our truck, which again, I always put the weight in the middle there, is 500 or 1,400 kilograms. Now, it is the force of gravity is acting on the object straight down. All right, and so again, that force is m times g, which in this case would be our 1,400 times 9.8, which is, let's see here, 20-some thousand? No, let's see here, 13,720. So this truck, pulls down with 13,720 newtons. That's how much it weighs. All right. Now, to counteract that, to lift this thing up, we have to counteract that force. So we have to apply a force of 13,720 newtons to counteract to get this truck moving. Now, initially, you have to do a little bit more force, but we don't count that. Again, perfect world here in physics class. But we have to counteract the force of gravity to move this truck up. Now, Again, I'm going to use my formula. For power is equal to force times distance divided by T. Now I know the power of this lift is 4,000 watts. All right. The force I have to apply, I know, is 13,720. Now again, this comes down to we need our distance. Our distance is the height, because again, the distance is just how far we're moving something. In this case, we're moving it up. So F is equal to H. They are the same thing. Or you could just leave it as D, knowing it is the distance straight up. And our time here is this happens in 5 seconds. All right, so I'm going to take, let's see here. Well, I've got a number equaling a fraction. I might as well do it right away here. Fraction equaling a fraction. Again, so I can cross multiply. So I have 1 times 13,720 times H. All right, then I got 5 times 4,000. Well, 5 times 4,000. Let's write it down here. Wait, it's just 20,000. All right, so then I get 13,720 H. 5 times 4,000 I know is 20,000. And of course, the last step here is to divide by my numerical coefficient, which is my 13,720 here. And the height I'm getting, again, it's going to be in standard units, so it's going to be in meters. The height that this object's been lifted is 1 point, let's see here, 46 meters. So about this high. I'm short. And there we go. So there's power. So again, it is looking at how fast you can work or how fast you can transform energy. It's the same thing, because working, you're putting energy just towards something, you're gaining or you're increasing its energy. In this case, we are increasing the gravitational potential energy of the object. And so that is what we're looking at. All right. So later on, shortly here, I guess, we are going to begin